Hello students, now we are going to study about simple harmonic motion, and also we are going to show the motion of projection of particle on any diameter performing uniform circular motion is simple harmonic. First we will see the definition of simple harmonic motion. A body said to be in simple harmonic motion if it moves to and fro about a fixed point, such that at any point acceleration is directly proportional to displacement. Nothing but what acceleration is directly proportional to displacement. I am taking acceleration as a and displacement as pi. Acceleration is directly proportional to displacement in magnitude but in opposite direction. That is called simple harmonic motion. So ఎప్పుడైనా ఒక ఆబ్జెక్ట్ సింపుల్ హార్మోనిక్ మోషన్లో ఉందంటే ఏం చెప్పొచ్చు, at any point acceleration is directly proportional to displacement. Acceleration అనేది డిస్ప్లేస్మెంట్కి డైరెక్ట్ ప్రపోర్షన్ ఉంటుంది బట్ డైరెక్షన్ మాత్రం ఆపోజిట్. Acceleration is directly proportional to displacement in opposite direction. This is the definition of simple harmonic motion. సపోజ్ మనకు కావాలంటే సింపుల్ పెండ్యులమ్ తీసుకోవచ్చు. ఇక్కడ సింపుల్గా తీసుకొని చెప్పిస్తాను నేను. ఇక్కడ సింపుల్ పెండ్యులమ్ తీసుకుంటే దీని మోషన్ ఇట్లా ఉంటుంది. యాక్చువల్గా టు అండ్ ప్రో మోషన్ చేస్తుంటుంది సింపుల్ పెండ్యులమ్. చేస్తున్నప్పుడు డిస్ప్లేస్మెంట్ ఈ డైరెక్షన్లో ఉంటే యాక్సిలరేషన్ ఆల్వేస్ డైరెక్టెడ్ టువర్డ్స్ ద మెయిన్ పొజిషన్. రిమెంబర్ హియర్ యాక్సిలరేషన్ ఇస్ డైరెక్ట్లీ ప్రపోర్షనల్ టు డిస్ప్లేస్మెంట్ బట్ ఇన్ ఆపోజిట్ డైరెక్షన్. ఇది ఎక్కడ డైరెక్ట్ అయి ఉంటుంది, ఇట్ ఇస్ ఆల్వేస్ డైరెక్టెడ్ టువర్డ్స్ ద మెయిన్ పొజిషన్. ఇక్కడ ఏముంటుంది, యాక్సిలరేషన్ ఇస్ ఆల్వేస్ డైరెక్టెడ్ టువర్డ్స్ ద మెయిన్ పొజిషన్ బట్ వెన్ యూ ఆర్ పుల్లింగ్ ద పెండ్యులమ్ in this direction, displacement is in this direction, acceleration is in opposite direction. So that's what we call simple harmonic motion. Next we will see motion on any motion of the particle which is performing uniform circular motion. For suppose a particle performing simple harmonic motion, its projection makes SHM. We need to prove that ఏదైనా ఒక పార్టికల్ సర్క్యులర్ పాత్లో మూవ్ అవుతుంటే దాని ప్రొజెక్షన్ SHM చేస్తానని ప్రూవ్ చేయాలి. If a particle moving in a circular path, we need to prove the projection of the particle is making SHM. We need to show that the projection of the uniform circular motion on any diameter is simple harmonic. So దీనికోసం ఏం చేస్తున్నాను నేను, consider a particle P which is moving in a circle of radius A. This circle has radius A and it is moving with some uniform angular velocity omega in anti-clockwise direction. In this direction it is moving. This is the direction of motion of the particle. Let O be the center and x dash and y dash be the diameter of the circle and n is the projection of P. ఇక్కడ మనం ఏం ప్రూవ్ చేయాలంటే, ఇప్పుడు పార్టికల్ సర్క్యులర్ పాత్లో మూవ్ అవుతుంది. పార్టికల్ సర్కిల్ పాత్లో మూవ్ అవుతుంటే, సో ఇక్కడ ఉన్నప్పుడు దీని ప్రొజెక్షన్ ఎక్కడ ఉంటుంది, ఇక్కడ y n ప్రొజెక్షన్. పార్టికల్ ఇక్కడికి వచ్చినప్పుడు ప్రొజెక్షన్ ఇక్కడ, పార్టికల్ ఇక్కడ ఉంటే ప్రొజెక్షన్ ఇక్కడ, పార్టికల్ ఇక్కడికి వస్తే ప్రొజెక్షన్ ఇక్కడ. అంటే పార్టికల్ అనే సర్క్యులర్ పాత్లో మూవ్ అవుతుంటే దాని ప్రొజెక్షన్ SHM. సో y డాష్లో మూవ్ అవుతుంది. n మూవ్స్ ఇన్ y డాష్. యాజ్ అ పార్టికల్ మూవింగ్ ద సర్క్యులర్ పాత్, ప్రొజెక్షన్ మూవ్స్ ఇన్ ద y డాష్ మీన్స్ ఇట్ ఈస్ మేకింగ్ SHM టు అండ్ ప్రో. సో అదే ఇక్కడ మనం ప్రూవ్ చేయాలి. Okay, let the particle n be the projection of particle P on y dash. See, as the particle P moves along the circumference of the circle, as the particle is moving circumference of the circle like this, you can see here, as the particle is moving circumference of the circle, its projection is moving along y dash. So the particle, as the particle moves in uniform circular motion, its projection is making SHM. We need to prove this by taking all the displacement, velocity, acceleration into consideration. Means by taking the definition of simple harmonic motion, we need to prove this. As a particle P moves on the circumference of the circle, n moves to and fro about a fixed point along y dash. So then it's a displacement find out. Just to find the displacement, let y be the displacement of particle at any instant. So this is the displacement I am taking, displacement y at any instant from triangle O and P. So this smaller triangle I am taking, from O and P. So this is theta. Then sin theta is opposite by hypotenuse. Sin theta equal to y by a and y equal to a sin theta, where theta is what, angular displacement. Angular velocity omega equal to angular displacement by time. Then angular displacement theta equal to omega t. We can write here y equal to a sin omega t, where theta is omega t. Next we need to find velocity. Velocity is nothing but what, the rate of change of displacement is called velocity. V equal to dy by dt. Then what is y value, a sin omega t. Differentiate this a sin omega t with respect to time. a sin omega t differentiation is a cos omega t, and omega t differentiation again omega. So finally we get velocity a omega cos omega t. Next, acceleration. Acceleration nothing but what? The rate of change of velocity is called acceleration. Acceleration a equal to dv by dt. We have velocity equation a omega cos omega t. Differentiate this a omega cos omega t with respect to time. Then we will get here. So differentiating the term to get acceleration. Acceleration a equal to d by dt of a omega cos omega t. So this a omega is constant, keep it outside. D by dt of cos omega t. This d by dt of cos omega t becomes minus sin omega t. Cos omega t differentiation, cos x differentiation minus sin x. Similarly, we are writing cos omega t differentiation as minus sin omega t. Again, omega t differentiation omega. Finally, we left with the minus and put the negative sign here. A omega into omega minus a omega square sin omega t. So this a sin omega t is what? Displacement y. So here we can write minus omega square y. Acceleration a equal to minus omega square y. So this equation represents what? General equation of simple harmonic motion, which is a omega square y. So this equation is coinciding with our general equation of simple harmonic motion. A is proportional to minus y. So the motion of the projection of the particle on any diameter performing uniform circular motion is simple harmonic. So this proves if a particle moves in a circular path, its projection makes a simple harmonic motion. Thank you. Hello students, now we are going to discuss about time period of the simple pendulum, and we are going to derive the equation for its time period. Okay, we will take a simple pendulum. Consider a simple pendulum of length L suspended from this rigid support. This pendulum is having the length L and it is suspended from the rigid support. When the pendulum is drawn aside by an angular displacement theta and released, it makes to and fro motion, means it makes oscillations in the plane at any extreme position. For suppose say at point A, at any extreme position A, the weight of the bob resolved into two components. One is mg cos theta and one is mg sin theta. So this mg cos theta is balanced by tension in the string. We can write mg cos theta equal to T, or else I can write T equal to mg cos theta. And we have another force mg sin theta, which is the unbalanced force which is responsible for motion of the pendulum. So this we call it as mg sin theta. This is called restoring force. The restoring force acting on the bob is given by F equal to minus mg sin theta. This negative sign indicates the direction. For suppose say if the displacement is in this direction, acceleration is in the opposite direction. So that is a basic definition of your simple harmonic motion. We can write a restoring force F equal to minus mg sin theta, and we know from Newton's second law F equal to ma. Substitute this ma here, this mm will get cancelled, we left with a equal to minus g sin theta. Then if theta is very small, so whenever we are taking the simple pendulum, the angular displacement should be very small, less than 5 degrees. So we can take the approximation of sin theta approximation. Sin theta, we can write expansion from sin theta expansion, we can write sin theta approximately theta for the small angles. Then we'll get a equal to minus g theta. This theta is what? Theta is arc length by radius. Arc length equal to radius into angle, or else if I want angle theta equal to arc length by radius. Here what is arc length? This y. This y is the arc length and radius is this L. Then we can get theta equal to y by L. Substitute this theta here in this equation. A equal to minus g into theta is what? Y by L. Then a equal to minus g by L into y. Rearranging the terms, we are writing g into the brackets and writing y outside to get the general equation form. And we have the general equation of simple harmonic motion, a equal to minus omega square y. Compare these two equations. This equation equation 1 and equation 2, we'll get omega square equal to G by L. This A is same, y is same. In place of omega square we have G by L. Then omega equal to under root G by L. And we have the equation for time period T equal to 2 pi by omega. We have the omega value here under root G by L. T equal 2 pi by omega. Omega is under root G by L. Then the fraction reverses here and we will get time period T equal to 2 pi under root L by G. So this is the equation for the time period of simple pendulum. We have the seconds pendulum also. Seconds pendulum. The pendulum whose time period is 2 seconds. Time period is 2 seconds. It is called seconds pendulum, and the length of the seconds pendulum is approximately 1 meter or 100 centimeters. 1 meter or 100 centimeters. This is about complete your simple pendulum and seconds pendulum. Thank you. Finding the length of the seconds pendulum. We know time period of seconds pendulum is 2 seconds. Take the equation of time period equal to 2 pi under root L by G. Squaring on the both sides, here we do squaring on both sides, then we will get T square equal to 4 pi square L by G. From this we get the equation of L as T square G by 4 pi square. T square, 2 square is 4 into G, 9.8 by 4 into pi square, 3.14 whole square. Approximately we will get 1 meter or 100 centimeters. So this is the equation, this is the value of length of the seconds pendulum. Next we will find potential energy. The work done against the restoring forces produces displacement in simple harmonic oscillator. So here work done W equal to average force into displacement Y. This average force F equal to F average, which is equal to 0 plus F by 2, because we are applying the force from 0 to F force we are applying, that produces displacement. Then we will get average force F equal to F by 2. So then work done becomes W equal to F by 2 into Y, and we know this force F equal to M A. In simple harmonic motion, acceleration A equal to omega square Y. I am not taking the sign into consideration here, taking only magnitude. F equal to M, A is what? Omega square Y. Then this work done becomes W equal to F by 2 M omega square Y by 2 into Y. Then we will get work done W equal to half M omega square Y square. This is the work done. This work done showed as potential energy P. Then we can write work done equal to potential energy, which is equal to half M omega square Y square. This is the potential energy, equation 2. Take this kinetic energy as equation 1. Now we need to find out total energy. Total energy is what? Sum of potential energy and kinetic energy. Total energy E equal to sum of kinetic energy plus potential energy. Kinetic energy, what is the kinetic energy? Half M omega square A square minus Y square. This is the kinetic energy, plus potential energy is what? Half M omega square Y square. In two equations we have half M omega square, take it common, half M omega square common, then we left with here A square minus Y square, here plus Y square minus Y square will get cancelled. We left with total energy E equal to half M omega square A square. So this is the total energy in simple harmonic motion. Total energy E equal to half M omega square A square. So we need to verify whether it is the same at all the positions or not. For that purpose, I am taking, first we will consider the case of main position. At main position, we will find the total energy at main position as well as at extreme position. So if we get the same value of energy, then we can say total energy in simple harmonic motion is constant. At main position, at main position displacement y equal to 0. If displacement y equal to 0, then what is the value of kinetic energy? Kinetic energy K equal to half m omega square a square minus y square. Then we will get kinetic energy K equal to half m omega square. This y square is 0, we will have to with only a square inside. So half m omega square a square. Then what is potential energy? Potential energy is 0. Why? Because you can see potential energy equation, potential energy is half m omega square y square. If y equal to 0, then potential energy is also 0. Then total energy is what? Sum of potential energy plus kinetic energy. At main position, total energy equal to sum of kinetic energy plus potential energy. Kinetic energy at main position is half m omega square a square plus potential energy is 0. So we will get total energy equal to half m omega square a square at main position. Next, if I consider this at extreme position y equal to a, at extreme position y equal to a, you can take as you are taking small a as amplitude, y equal to a, then kinetic energy K equal to half m omega square a square minus y square. Put y equal to a here, then you will get kinetic energy K equal to half m omega square. This y equal to a, it becomes 0, a square minus a square 0, kinetic energy 0 at extreme position. Then what is potential energy? Potential energy P equal to half m omega square y square. So this y equal to what? A at extreme position. Potential energy P equal to half m omega square a square. And total energy equal to what? Sum of kinetic energy plus potential energy. Kinetic energy is 0, potential energy is half m omega square a square. Then we get total energy at extreme position is half m omega square a square. So the energy at every point, so at extreme position or main position, which is half m omega square a square. At extreme position, kinetic energy is 0, potential energy is half m omega square a square. At main position, potential energy is 0, kinetic energy is half m omega square a square. So total energy, these two are tallying with total energy, right? So total energy in simple harmonic motion is constant. So if we draw the graph, of kinetic energy and potential energy, we will get it like this. One graph is like this, one curve, and another curve is like this. So this is a graph of kinetic energy at main position, kinetic energy graph. This is a graph of potential energy. Kinetic energy at main position, kinetic energy is maximum and potential energy is 0. At extreme position, potential energy is maximum and kinetic energy is 0. They take this as minus a and plus a. So this is a graph representing kinetic energy and potential energy. So this is the total about energy in simple harmonic motion. Thank you.